Hello again, everybody. Dr. Richard Smith here with the Foundation for the Study of Cycles and Cycles TV. And hope everybody's having a great week, enjoying the relief rally. We'll see if it lasts. I am going to continue my exploration today, and I have more questions than I have answers. But you know, I actually think the secret to getting better at things is asking better questions, not just buying answers. Buying answers doesn't work. We need to be asking better questions. And I hope that is what the Foundation for the Study of Cycles increasingly is about, asking better questions, because I do think that cycles are something that we don't understand. I'm starting to understand them in some ways that I have not understood them before, and I'm really excited about it. And I hope to continue to share what I'm seeing with you, and you help me to ask better questions. You know, when you ask better questions, you get better answers, right? But you do have to go through the process of asking better questions. So with that as preamble, let me know that you're with me today, and love to hear who's checking in and from where, so don't be shy. And look, this is different ground than I've been covering for the last couple of years. I'm going to be delving into a little bit of math, even the math of complex numbers. So don't freak out. We'll get through this. But I think when you start to see what I am seeing, you can help me. We can help each other to see the world in a new way, ask better questions, and get better answers. Okay? So with that as preamble, I am asking your patience. Let's go. All right, so let me begin by first revisiting. Well, give me just a second here. Okay. All right, let me see what you're seeing. Okay, so last time we were together, we started to remember something that science has largely forgotten. It's not that we've forgotten how to estimate the spring and neap tides, right? When the tides come up to their highest over the course of a month, and when the tides go down to their lowest over the course of a month. The spring tides are the high tides, the highest tides, and the neap tides are the lowest tides. And the spring tides occur when the sun and the moon, okay, in a relationship to Earth, are either on either side of the Earth and 180 degrees, or we're on the same side of the Earth here at 90 degrees. 0 degrees. And then the neap tides occur when the sun and the moon here are in 90-degree relationships. Okay, so over here, we have spring tides. The orange vector here is the sun's gravitational influence. It's smaller because it's so much further away. And the blue vector here is the moon's gravitational influence. And when they're both pointing in the same direction, they create max tides at the new moon, okay, the highest tide. The new moon is here. They happen to also create high tides at when that, let's say that orange vector is over here, pointing in the opposite direction. When they're in a 180-degree relationship, that combined pull still creates the spring tides. That's at the full moon right here. And then when the sun and the moon are in this 90-degree relationship here, we get the first quarter neap tide, and then say when that orange vector is pointing down, when the sun's force is pointing down, then we get the third quarter neap tide. So this is the way that the tides are influenced by the sun and the moon, the gravitational forces expressed through the sun and the moon as masses to create unobservable in our world, namely the tides. Okay, the tides are what in physics is called unobservable. We can observe it, right? We can sense it, we can see it. So I think about physics a lot, and observables in physics are a big deal, right? We'll get into quantum physics sometime down the road. I have a lot to say about it, but it's a little much for today. So let's continue to just get oriented in this world of phase, okay? These are phase relationships. And I'm going to try to continue to develop your intuition and my intuition for what phase relationships mean. You know, what are they? And why have we neglected them or not paid attention to them for hundreds of years now? Right? I'll establish that thesis as we go along. They basically have to do with what in the math world are called imaginary numbers. Imaginary is a term applied by René Descartes of Cartesian geometry, the Cartesian coordinates. Maybe you remember that from math. And the imaginary numbers have to do with the square root of -1, whatever that is. And Descartes said, I don't know what the square root of -1 is, so I'm going to call it imaginary. And then I'll call these other numbers the real numbers, the ones that if I make a measurement, I can get a number out, and that number is real because it has a physical counterpart. It can be connected with something observable. The imaginary numbers can't be connected with something observable for some pretty deep reasons that we'll get into eventually. But the real numbers can be connected with observables, so they can be connected to physical theories that the physicists developed. And Descartes and all of the mathematical physicists since Descartes would rather not really deal with imaginary numbers. But to make a long story short, imaginary numbers refused to be banished forever from our scientific vocabulary, and they popped up again in quantum physics, of all places. Quantum physics, waves, particles, right? Waves have to do with what? Gravitational waves, electromagnetic waves. They have to do with phase. They have to do with relationships, and that is expressed through complex numbers, which include the imaginary numbers or integrate the imaginary numbers. The complex numbers are really the combination of the real numbers and the imaginary numbers. So I'm going to watch somebody else's video here for just a few minutes to give us a sense of what happens in the complex numbers versus the real numbers. And you're going to see in just a few minutes how this really illuminates the world of cycles. So this is a video by this 3 blue, 1 brown gentleman who does these fantastic videos really to illuminate mathematics visually. He's got 8.26 million subscribers, doing a good job, kind of similar to Veritasium, right? Big popular science and math channel. And he said this video here is what is e to the t. So just watch a few minutes with me. I'll explain it after he finishes. So if you lose track, don't worry about it. I'll help you catch up. But his question is, what is e to the t?
Is to ask, what properties does it have? Probably the most important one, and from some points of view, the defining property, is that it is its own derivative. Together with the added condition that inputting 0 returns 1, it's actually the only function with this property. And you can illustrate what this means with a physical model. If e to the t describes your position on a number line as a function of time, then you start at the number 1. And what this equation is saying is that your velocity, the derivative of position, is always equal to that position. The farther away from 0 you are, the faster you move. So even before knowing how to compute e to the t exactly, going from a specific time to a specific position, this ability to associate each position with a velocity paints a very strong intuitive picture of how the function must grow. You know that you'll be accelerating, and at an accelerating rate, with an all-around feeling of things getting out of hand quickly. And if you add a constant to that exponent, like e to the 2 times t, the chain rule tells us that the derivative is now 2 times itself. So at every point on the number line, rather than attaching a vector corresponding to the number itself, first double the magnitude of the position, then attach it. Moving so that your position is always e to the 2t is the same thing as moving in such a way that your velocity is always twice your position. The implication of that too is that our runaway growth feels all the more out of control. If that constant was negative, say negative 0.5, then your velocity vector is always negative 0.5 times your position vector, meaning you flip it around 180 degrees and scale its length by a half. Moving in such a way that your velocity always matches this flipped and squished copy of your position vector, you'd go the other direction, slowing down in an exponential decay towards 0. But what about if that constant was I, the square root of negative 1? If your position was always e to the it, how would you move as the time t ticks forward? Well, now the derivative of your position will always be I times itself, and multiplying by I has the effect of rotating numbers 90 degrees. So, as you might expect, things only make sense here if we start thinking beyond the number line and in the complex plane. So even before you know how to compute e to the I times t, you know that for any position this might give for some value of time, the velocity at that time will be a 90-degree rotation of that position. Drawing this for all possible positions you might come across, you get a vector field, where, as usual with vector fields, you shrink things down to avoid clutter. At time t equals 0, e to the it will be 1, that's our initial condition, and there's only one trajectory starting from that position where your velocity is always matching the vector that it's passing through, a 90-degree rotation of the position. It's when you go around a circle of radius 1 at a speed of 1 unit per second. So after pi seconds, you've traced a distance of pi around. So e to the I times pi should be negative 1. After tau seconds, you've gone full circle. E to the I times tau equals 1. And more generally, e to the I times t equals a number that's t radians around this unit circle in the complex plane.
All right. So I know that's probably more math than you bargained for today, but I just want to go back here and look at this, right? So the imaginary number, square root of -1, has to do with rotation, with cycles. When you multiply with complex numbers, what you do is rotate. When you multiply with real numbers, what you do is scale, right? And we live in a world that is obsessed with scale today and has forgotten all about rotation. And rotation really has to do with relationships. The rotation of the sun and the moon, at different angular relationships produce the observable known as the tides. Okay, gravity operating through the sun and the moon, depending on their angular relationship, right, produce the spring and neap tides and everything in between, and they create what are called interference patterns. So let's go back here, see if we can understand this a little bit better now. Maybe I can reset this and just kind of step. Here's the sun and the moon where they're kind of moving together, right? But their angles are changing slightly. but they're pretty aligned. So their combined gravitational pull on the tides is creating the high tides, which you can see in a tidal gauge over here. Okay, but then as the month progresses and the angular relationship changes between the sun and the moon, okay, they start to get more of an angular relationship, right? We can actually slow this down and just play it, okay, until they get to the point where they have a 90-degree relationship. Right? So gradually the angular relationship changing is diminishing the overall gravitational influence on the tides. Okay, so up to about here, I think. Well, actually, I guess this is expressed, right, as, I think when they're in opposition to each other here, that's the 90-degree mark. Okay, so that's the neap tides. So now they're at a 90-degree relationship in opposition as vectors. So that's the idea of the spring and the neap tides, again, producing the sun and the moon interacting, creating an interference pattern that produces the spring and the neap tides. So now I'm not sure if this is fully operational or not. Let me see here. Yeah, okay. So this is the idea. If we go back here and we say, well, you know, we've got this curve here. This is a time series. And we want to know what is causing this time series. Okay, think of this as a stock price chart. Okay, goes up and down and up and down. This could be the S&P 500, right? It's a time series. It's measurements of something, measurements of an observable over time at usually equal units of time. So what are we trying to do with time series analysis? We're trying to forecast the time series. And so here we have a time series of the tides recorded over time, and we have an explanation of two influences, the spring tide and the neap tide. Sorry, not the sun and the moon, sorry. The influences of the sun and the moon combining to produce the results. So right now in cycles analysis, right, we typically focus on a single asset. So here's oil. Not sure if this is totally current or not, but we could refresh it. Here's USO, right, the ETF that tracks the price of oil. And in cycles analysis today, we've primarily been focused on how do we use cycles to analyze a single time series. It would be kind of like if we were just looking at this, we want to forecast this, and all we're looking at is the sun, and we don't look at the moon. So there is a lot that you can learn from how the sun moves that would help you forecast this line. But what if you could look at the sun and the moon together? You get more information. The sun and the moon in this case are coupled oscillators. They are coupled, and together their combined influence, their coupled influence produces the tides. So I think that this is the kind of analysis that Dewey and our other illustrious predecessors were engaged in. Now, as far as I can tell, they didn't really talk about complex numbers or phasors or coupled oscillators. But as I've spent more time in the archives, I can tell you that that is what led me to, in part, to this line of inquiry. So if we just look at USO here, right, we can see, obviously, it's got a lot of red. All the cycles are quite stretched. In fact, they're all red or turning red, right? So looks quite dramatic. But, we've seen this before. This happens when something interferes. In this case, war in the Middle East, pushing oil prices to an extreme and not really letting up. So the cycles can certainly help us here. We can see what the most stable cycle has been over time. We can see its strength. We can see its clarity in the spectrum here, right? But the question I'm beginning to ask myself is, what if oil is coupled to other asset classes? The most obvious one to me is the dollar, the US dollar, the petrodollar, if you will, right? So what's happening in the relationships between oil and the US dollar, okay, that might potentially impact other asset prices or each other's asset prices. So if we look at the US dollar, okay, I think it's dx-y.nyb. Let's see if this works. Yeah, okay. So here's the dollar. And we can see that the dollar has a cycle of 169 days right now. And oil has a cycle of 159 days. Oil is at the top of its cycle, and the dollar is not at the top of its cycle. So if we go over here now, again, this is a work in progress, okay? Using our cycles detection technology together with, in this case, Claude, to help me visualize things in a new way, okay? Actually, the number one dominant cycle here is the 90-day cycle by rank, right? It's got the sharpest spectral presence, whereas this 169-day cycle tapers off a little bit. So this process of choosing which cycle you're going to focus on is very important. And it's a ongoing process to decide on the best method for you and your purposes, whatever you're trying to understand through cycles, which cycle to pick. But right now, as far as I've gotten, it's just using the number one dominant rank cycle from each asset. So in this case, it's the 90-day cycle on oil. Actually, let's put that back up here. And it's the 159-day cycle on oil, and then the 90-day cycle on the dollar. So, right now we can see that let me just zoom in here a little bit. So this is a little hard to see, but there's a circle here, okay, just like we saw for the tides, okay? And this is they move around here in different angular relationships, and you have the max when they're aligned, and the minimum or the reduced when they're in opposition. And you can see the same thing here, the top, a rising, the bottom, okay, and falling. So and then this here, this gray bar here, is kind of the combined result, or the combination of these two vectors for oil and the dollar. Okay, again, following that same idea of the spring and of the sun and the moon and their angular relationship. All right, so I'll try to crisp up some of these colors a little bit to make them easier to understand, but we can now kind of step back a little bit in time. Okay, so here's the price of oil here. And this dashed line is telling us when are those cycles between the dollar and oil, coming into an alignment and reinforcing each other, right? And it did happen. I'm calling this coherence. It did happen right at the bottom of the price of oil. So when the dominant cycles for the dollar and oil both came into alignment with each other, right? And in this case, they were both rising together. You got a bottom in oil prices. Do I know if that is very meaningful? I don't know yet. I don't know. This is all new research, okay? But as we move forward now in time, let me see if I can't play this too slow, but you can see that they're diverging and then they're getting into an opposition there, right? Now they're at a kind of, their coherence is decreasing, right? They're kind of opposing each other. They're at a oppositional angular relationship, and that coherence is moving down. So this is the idea. Let me just stop for a minute and come back. This is new stuff, guys and gals, right? So it's a new way of thinking about cycles. It's not really new, actually, but it's something that we haven't focused on very much in the last few decades. But I do think it's the kind of thing that we see more of in the archives dating back to the founders of the foundation. What are the common cycles that we see across different time series? Not just forecasting a single time series, right? Maybe you want to forecast the tides, and maybe there is some analog of the tides in the markets that we can say, what are the coupled oscillators in the markets that are producing the market tides? Okay, that's a legit question. I'm not there yet. I don't have the answers yet, but I think this is a good research direction. And I think that, looking at the dollar and oil, for example, what are their strongest cycles? What's the harmonic relationship between those cycles? And, what's the phase relationship between those cycles? So could we begin to have a complementary approach to cycles analysis where we're not just focused on optimizing, how can we use all the cycles we can find in a single time series to better forecast that time series, but how can we look across asset classes and find the cycles that are shared across asset classes, that are coupled across asset classes, and then how can we study those couplings to better understand the market tides, whatever those market tides might be. So that is the direction that my research is taking me. That's what I'm working on. I'm actually calling this cyclics to distinguish it from physics. physics is mostly concerned with particles and scale, and cyclics is concerned with rotation and return, closure, things that have been ignored by physics, systematically ignored for centuries now. And I really think this is part of what was behind why the chief economist of the Hoover administration, the head of the Smithsonian, Harvard astronomy and Yale geology, et cetera, wanted to better understand cycles. And I think we're in a place today where we can study cycles in more interesting ways than we've been able to study them before. So that's the direction I'm going. Let's see if anybody's got any burning questions here. Jesse, I can only imagine what the next 10 years of learning cycles will result in. Me too. Me too. A lot of these terms remind me of sound production for music. Absolutely, right? Phase nullification and phase amplification of frequency, hertz or cycles. Yes, there's a reason, music is often associated with harmony, relationships between vibrations. Okay. All right. So that's really what I have for you today. Again, I don't have answers. I have more questions than I have answers. We're at about the 30-minute mark, but this is what I'm working on for the conference. Gonna be talking on cyclics, the science of cycles. I think that there's a lot that we can do with this complex number, imaginary, rotational, relational approach to understanding our world. And I think that's what cycles really can help us do. Cycles are pointing towards something that we've been missing, right? And they're pointing towards that rotation, which interestingly, I'm not a physicist, I'm not a quantum physicist, but the complex numbers are a big part of what's called the wave function in quantum physics. And the wave function doesn't quite mesh with the observables in our world in the way we expect it to. So there's something different about complex numbers and real or scalar numbers that don't quite explain each other. There's a gap there. There's a gap between wave and particle. I happen to think both wave and particle are very important. One doesn't preclude the other. They're both necessary. And so, systematically studying how we can use complex numbers, complex number geometry, breaking down, factoring phase relationships between coupled oscillators to help us better understand our world. That sounds like a worthwhile thing to do together. All right, everybody. If you're watching this later on, please put your questions, comments for me in the here on YouTube. Tell others about this because we need to ask better questions. And we need to ask better questions together. I think this actually explains something too about the relationship between human intelligence and artificial intelligence, because artificial intelligence is all based on scalar mathematics, no rotation. We provide the rotation. We provide the return. We close the loops in a way that artificial intelligence does not. And if you've used artificial intelligence for more than 2 minutes, it's always extend, extend, extend. It can never just rest. It can never not have a next question. It has to always just keep you moving, 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 moving. There's no rest ever. That's the nature of a scalar real numbered observables only world. You know what? There are unobservables. They exist. So, food for thought. I'll look forward to following up with you next week. Have a great week, everybody, and be careful out there. Bye.
Cycles matter because they show us the future. Nothing else shows us a future path. Nothing that I've ever found in over 60 years of doing this.
The foundation is bigger than markets, right? It started out bigger than markets. It's still bigger than markets. It's bigger than us.
There is no such thing as a black swan. It is merely a cycle that was not forecast or anticipated.
To me, it's huge. If I can get a glimpse of the future, just a little bit of the future, I'm way ahead.
I think that the Foundation for the Study of Cycles has a role to play in both bringing technology to the world, but also really emphasizing agency and human agency.